pleasure to welcome you to the third installment of our series on ethical and social considerations in AI. This week's speaker is Kilian Weinberger. Kilian is a faculty member of the computer science department here. He just joined us last year from University of Washington, St. Louis. Kilian is a leader in the area of deep learning, and that's what all the buzz is about these days, and that's what tonight's talk will be about. Kilian's going to be the program chair of the next big AI conference next year, and was also program chair of the Machine Learning Conference a year ago. So shows sort of what the community thinks of him and how much of a leader he is. But rather than taking his time, I'll let him start. Talk about deep learning and interpretability.
Hello. Thanks, it's an honor to be here. One thing I see is a lot of people from my class here. That's awesome. That's really great. Some of the material is actually taken from my class, so just pretend you haven't seen it before and just, please laugh at the jokes just as if it's the first time. Okay, so I'm talking about interpretability today, but actually I want to start with just a little overview of what machine learning actually is. Actually, can we switch this light off? So this is really bright. No. Okay, all right. Can you see this in the back? All right. So what is machine learning? And well, from a really, really high bird's eye view, let me just tell you what traditional computer science is and how machine learning differs. So traditional computer science, you have a computer, that's this thing in the middle, and you have some data that you want to process on that computer, and you want it to generate some output. And the way you typically do this is, you as computer scientists, you write a program, right? So for example, let's say the data is an MPEG-4 file or something, some video, right? Then you look up on Wikipedia what the file format of an MPEG-4 is, how it's encoded, and over a long weekend you write up some code, right, that basically reads in that file and generates basically stuff on the screen that's actually the movie. Right? That's not the kind of data that I'm interested in or that I'm confronted with. So the kind of data that I see is something like this, right? Where someone from the medical school or some colleague comes to me and says, here's an MRI scan, this is an fMRI scan of a person, and I would like to know, does this person have Alzheimer's, yes or no? Right? And so the problem is I have absolutely no idea how to write such a program. Right? If I knew, I would have know a lot more about Alzheimer's than I do. I really don't know. In fact, nobody knows how to write this program, right? Because we don't know how this actually works. But it turns out, we don't just have this one image. Turns out actually there's, doctors have taken many, many images of people with Alzheimer's. And so, one thing we can do, we can actually take these other images that have been taken in the past, and in those cases, we actually know what the answer is, right? So in those cases, we know if the person had Alzheimer's or not, right? So let's say 5 years ago, someone took an fMRI scan of someone. 5 years later, now, it's actually obvious, yes, that person actually, turns out, does have Alzheimer's, and that should have been visible 5 years ago. So what we can do is the following. We can take this data that was collected before, right? So this is old data. But the nice thing about this data is we know the answer, right? We know, yes, this image is of someone who has Alzheimer's, this image is of someone who doesn't have Alzheimer's, and so on. Right? And what machine learning does is you take this data for which you know what the output should be, and you generate a program. Okay? So machine learning basically takes as input the data and the output and generates the programs. And that can literally be a program. Right? So it can be C code or something. Most commonly, it's not. Most commonly, it's just a string of numbers that then can be interpreted as a program. But you could generate, actually interpretable, actually not interpretable code. And then what you do is, of course, then you go back to the image that you're actually interested in, and you use the program that you just generated, and you stick it in, and now it generates you some output. And hopefully, if that image is similar to the, the images from your what we call the training data, then it will give you a good prediction. One criticism of machine learning, and this is what what the talking part about will be about, is that we don't know. Nobody has actually written that program, so we can't ask any humans questions about it. And this is what I will get into later. Is like, what can we say about these programs? One of the early moments where people realized the potential of machine learning was in 1994. With T.D. Gavin. So this is was a famous moment where Jerry Tesaro, who worked at IBM, wrote a game player to play backgammon. Backgammon is a game that's actually very, very popular. It's one of the most popular games in the world. It's not popular in the United States, but in other places it's very popular. And so in 1994, the way people wrote game players is you use the minimax algorithm. And to this day, it's a very popular algorithm. The minimax algorithm just takes, basically what it does is basically just tries every single move and then flips the board and said, if I would make this move, then you could make this move, and then I would make this move. And it basically goes through it like 10 times, and at the end said, well, that would look better for you. And so it tries out all possible moves. That's an algorithm that's really, really slow and has to, basically because it has to try so many combinations, takes forever. So Jerry did something else. He took an artificial neural network and let the artificial neural network decide which move to take. Right? So it programmed all legal moves, and then the neural network chose which move to take. And it let it make moves and played against it, and the neural network was horrible, right? Of course, right? How would it know how to play? But then he did something that was really, really awesome. He took the neural network and let it play against itself. Right? So basically 2 copies of the identical program, and let it play against itself, and then one of them always wins and the one always loses. And so what he did is the one that wins gets positive feedback, and the one that loses gets negative feedback. And so he put that in an infinite loop and went home. And the next day he came back, and the game had now the program had now played several 100,000 games against itself. And he stops it and starts playing against it. And the amazing thing is he has no chance. Right? The neural network beats him. And he goes around his office, right, and asks other people, like, look at this, right? Play against my neural network, right? And nobody has a chance. So he gets really, really excited, right? So what he did is, first of all, he continued that infinite loop and let it play a few more million games against itself. But then actually he contacted the World Championship organization in backgammon and asked them, can I get, I have this program and I think it's really, really amazing. Can I get time with the world champion in backgammon? And they were curious, and they gave him time with the world champion at the time. He met up with him, and it turned out the program won. Right? And people were amazed. They were like, wow, how does it do it? Right? And he's like, I have no idea. Right? It learned it itself. In fact, Jerry doesn't know how to play backgammon that well. Right? The program really learned it itself. And since then, people have used machine learning for many, many, many different tasks, right? And you probably use them every single day for search engines, mail spam filters, etc. So machine learning is now, everywhere in your life. And it's not now just, in everyone's lives now. It's also actually in science. Right? So that's what we call data-driven science. So historically, what people do in science is they try to explain some complicated phenomenon, and they come up with some model. And then what they do is they make experiments, conduct experiments, collect data, and they try to verify the model that they came up with. So this is what people have been using ever since Galileo. Data-driven science does exactly the opposite, once again. Right? So basically what you do is you collect data, and then from this data, you try to construct a model. Right? And this can literally work, actually. Right? There's a famous paper, actually, here from Cornell, from Hart-Lipson, where you actually took a pendulum and let it swing, and let a camera observe that pendulum, and let the computer by itself figure out fundamental laws of physics by literally just watching the pendulum. By the way, if there's any questions, please interrupt me. Please feel free to interrupt me. So the question is, how does machine learning work? And while I give you a 3-minute introduction on actually in specific deep learning, so there's many different ways of machine learning. There's statistical machine learning. There's machine learning that's based on optimization. And what I will look at is machine learning in terms of function approximation, and something that people lately call deep learning. That goes back, was actually invented a long time ago. And it was invented here at Cornell, actually, by Frank Rosenblatt in 1957. This was the very first neural network. It wasn't called that at the time. It was called a perceptron. And that was, arguably also the first classification algorithm. Here's how it works. So imagine you have data. And so, I'm giving you an example now that obviously Frank Rosenblatt didn't have back then. But, so you have emails, and you want to know, is an email spam or is it not spam? Okay? And so what we do in machine learning, we typically take our data and we represent it as a vector in some very high dimensional space. So for example, with emails, what you can do is you can construct a long vector that counts how many times a given word is present in your email. So there's maybe a 1 million dimensional vector or something. And you give them two different labels. +1 are the ones that have spam, and -1 are the ones that are not spam. So what does the perceptron do? The perceptron is a very simple algorithm that says in this high dimensional space, let's position a hyperplane. Right? So in 2D, this is just a line, such that all the points of one class lie on one side, and all the points of the other class lie on the other side. Right? And the magic behind the perceptron was, and this was at the time really revolutionary, that Rosenblatt came up with an algorithm that actually provably finds such a hyperplane if it exists. And turns out in very high dimensional spaces, actually, that always exists pretty much. So you use the perceptron algorithm to position this hyperplane, and then when a new email comes along, you just have to look into which side of this hyperplane do you lie on. And so in mathematics, it's just the hyperplane is defined by a vector. You just compute the inner product with that vector. So if that's positive, you lie on this side. If it's negative, you lie on that side. And that's all there is to it. So during test time, it's a very, very fast algorithm. And actually, it's used to this day. So just to explain this in terms of, people draw this as a neural network. If you draw it as a neural network, then basically what you do is you have the different input dimensions of your, a vector x, which are these dots here. So for example, these could be the counts of the different words in your email. And what you do is you multiply them by some weight. And you sum that up, that gives you the output. That's the same thing as this inner product notation. Okay, good. So this was in 1957, and it was a big deal. It was all over the news, etc. But actually, it's pretty limited. And why is it limited? Because if you're in a low-dimensional space, drawing a hyperplane, just a line, may not be enough, right? You could easily imagine that the blue point lies here. Well, then actually, there's no line in the world that would separate the red points from the blue points, right? Because you have a blue point over here. So what are you going to do? Right? So Rosenblatt thought about this for a couple of years, and he extended it. And he called it the multi-layer perceptron. The multi-layer perceptron is exactly the same thing as an artificial neural network or as a deep learning algorithm or a deep net. These are all just different words for the same thing. So what he did is very simple. He basically said, well, if I want to extend this to nonlinear decision boundaries, what I do is I take my input x and I multiply it by a matrix. So basically I have an affine transformation. I kind of, what this does in some sense is it takes certain dimensions in the space and it stretches them, right? And others it can push us together. That's all that's going on. And then I have some function here that is nonlinear. And what people nowadays use is just take the max with 0. So everything that's negative, I just forget about it. I only keep the positive values. That's called a rectified linear unit. He back then did something else. He back then used the sigmoid function because he wanted to build something like the human brain. So he tried to model this. Turns out actually it's much, much simpler just to take the max with 0. And then after this, you just stick it in a regular perceptron. So then you just do a linear update. And again, there's an algorithm that's called backpropagation that was actually invented a couple of years later to learn this efficiently. What the algorithm does, it learns this matrix and this matrix such that basically you learn a decision boundary so that points of one class are on one side and points of the other class are on the other side. This is, in some sense, most machine learning algorithms can actually be written in one form or another in this kind of paradigm, like as some kind of neural network. And so machine learning people are always kind of interested in how can you make machine learning algorithms more powerful. And so for the last, let's say 15 years, or let's say 10 years until 5 years ago, so during all the 2000s when I did my PhD, people tried to make these algorithms more powerful by making this layer here wider. So this is actually what support vector machines are. So in case you've heard of support vector machines, they actually make this here infinitely large. Right? So that is a mathematical trick how you can still actually compute it, even if you have infinitely many dimensions here. And that makes networks really, really powerful. That was the paradigm until, 5 years ago, maybe a little bit before that. And then something interesting happened. And what happened was that GPUs came around. And GPUs became very, very cheap. So GPUs are basically graphic cards for gamers initially, but actually turns out that they're very, very well suited for matrix multiplication. And so in here I have a matrix vector multiplication, which can be done really, really fast on one of those gaming cards. Right? And so what actually Jeff Hinton famously did, he was one of the first to kind of realize the potential of this, and he bought a whole bunch of these GPUs and actually spun off a company, and basically said, well, with all these GPUs, we can do a lot of matrix multiplications. In this case, it doesn't actually pay off anymore to make this really, really wide. What we should do instead is we should make this really, really deep. So what we do is we actually don't just have one layer here, we actually have many different layers. So we multiply with many, many matrices over and over again. This was something that Rosenblatt had thought of before, that you can actually make, introduce many, many layers. Right? But it turns out there's a famous theorem that shows that you never have to do this. Theoretically, there's no need for you to ever do this. Like everything you can learn with such a network, you can always learn with just one layer that's really, really wide. So it seemed much more reasonable to just make these really, really wide. But now that GPUs came around and were so cheap, actually this was no longer expensive. You could actually compute these deep networks very, very fast, and suddenly became very, very fashionable. And well, if you've been reading the news in the last couple of years, or I'm sure you've seen any of these algorithms, that's basically the crazy success that deep learning has had. So suddenly, problems that used to be really, really hard suddenly became really, really easy. Right? And I'm not going to go into this, why this is the case. So it turns out, actually, if you have many of these layers, it does actually help you a lot in practice. In theory, actually, it doesn't help you. Like, theoretically, there's no proof that shows that that's actually an advantage. But actually, we are very good at intuitions why it helps you in practical settings, and that's depends on, there's many good reasons why that is the case, especially actually for images. Yeah, sorry, yeah.
Isn't there a concern about overfitting?
There is a concern about overfitting. So what is overfitting? So overfitting is, initially I had this example with the MRI scans, and I said, well, I show you images of people where I know this person has Alzheimer and this person doesn't have Alzheimer. Well, one thing the machine learning algorithm could do is it could just memorize, right, which person had Alzheimer, which person doesn't have Alzheimer. Basically, for example, based on the form of the skull, right? That works, but it wouldn't generalize to any new people, right? So usually, you're totally right. Machine learning theory says the more parameters you're fitting, the more likely you are to overfit, and you have to do something against it. Now, it turns out the way these deep neural networks, and they have many, many parameters, so you're totally right, but the way they're trained is actually with an algorithm called stochastic gradient descent. And what that does is makes, it gets a little bit technical now, but what it basically says is ultimately it doesn't find any solution here. It actually finds a very specific solution that is very constrained. So, so it's not actually that these matrices can take on every possible value. You actually effectively have much fewer possibilities than you should have. Does that make? Yeah, we can talk about it more offline. It's a good question, though. Any other questions about deep learning? Okay, so this baby says it's getting boring. So let me show you a demo. One second. Just need to. Okay, so what I thought is I just show you quick examples of neural networks, just that you can visualize visualize a little bit. So the first thing I want to show you is actually just a little example of the Perceptron. This is the algorithm that was invented in 1957. And so here's what we do. We just take some data points in 2D. These are the positive points. These are the negative points. Here are the positive points. And what the Perceptron does now, it basically, one second. So it basically starts with some hyperplane. Here is the plane that says, OK, I would like to find a line such as all the positive points on one side, or the negative points on the other side. Right? This is clearly not correct. This guy is wrong, this guy is wrong. So it picks one point that is wrong and makes an update so that this point is now classified correctly. So it moves the hyperplane. And that's what it does. And actually, in this case, it's already done because this is a really simple example. Right? So now actually all the positive points on one side, all the negative points on the other side. And the beauty about the Perceptron is that you can prove that if a hyperplane exists, you will actually stop after a finite number of iterations. So there's only it will not go infinitely, which is an important property. Just to actually get the here's one more example just to actually introduce this concept. This was classification, so you try to find a hyperplane such that the positive points are on one side, the negative points are on the other side. Another setting that's been known in statistics for many, many years is regression, where you actually say, I have data points and I would like to find a hyperplane that basically a function that basically best fits these data points. So in this case, I have no two classes, I just have one class, and I would like to find some function that explains this class. In this case, basically, you find a line that says, here, I think, my data points basically roughly lie on this line, right? So the relationship between x and y is basically roughly the relationship of this line. These algorithms are tightly related, and so one is called regression and the other one is called classification. So let me show you an example of actually a neural network. So, second demo one. Yeah. Okay, so here's the same problem. So I'm trying to have these data points here. I just draw them anywhere I want. And now I can say fit a neural network. This is basically this multi-layer perceptron to explain these points. And I can run it, and this is what it gives me, right? And so what the neural network does in this case, actually, it finds many, many linear functions that approximate this data set, right? So what you have, the numbers I have here is basically I have 40 hidden neurons in the middle, and then another 40. So I have 2 layers of 40 neurons. Any questions about this demo? Yeah?
So what do the hidden parts do, like in the email versus in this?
They basically make that these lines don't just there's not just one straight line. So what these hidden nodes in some sense say is say we have many different lines that we can switch on and switch off. And by doing this, you can actually say, here's my first line. Now the second line comes in, right, which now makes it a little bit steeper, and so on. So all of these basically are functions, and because I always have this max operator that max was 0, whenever they become negative, I just set them to 0, which essentially just means I switch them off. So I have many, many functions that I can switch on and off. And by this way, I can actually combine them to kind of take any shape. That's the high-level idea. I can maybe show this actually on here, 1D plus. All right, here we go. This is the demo. Here I have a data set, and what I'm doing is I actually increase the capacity of the network. So initially, I just have 2 nodes. So in this case, actually, you have a very, very simple neural network. So it tries to explain this data, and all it can do is basically have some linear function here, some linear function here, and some linear function here, and that's all it does, right? That's all all it's capable of. Now I can increase the number of neurons I have to 4, and it already has a much, much better fit of this data, maybe, right? This could also just be noise, who knows? And what's the scary part is this part here, right? So what scares people is, in this part where there's no data, the function in some sense can do anything it wants, right? And that's why people would like to get more interpretability. All right, so and as I increase the capacity, it keeps going up and fits the data more and more. I would actually have one more kind of more fun application that this is all. I mean, I look at you and you're like, well, this is just some dots. What is this? All right, so let me show you some something more interesting. Okay, so I thought of some really. I hope I'm not offending anybody here. Some really challenging talk. This is on ethics. So let's say do something ethical questionable. So here's. I hope Joe and Bob will still talk to me afterwards. So here's the idea. So I thought, well, let's come up with some really, really hard task. Right? This is not going to convince you that neural networks are really, really awesome. So here's some really, really hard task. Right? So here's what I did. So turns out there's this web page where people can upload their own photos, and other people can go to the web page and they can say if you're hot or if you're not hot. And so what I thought is, well, this is actually great, right? So now we have these images of people, and we actually have thousands of votes if the person is hot or if they're not hot. And so I thought, well, can we train a neural network to predict if someone is good looking or not? right? This is a really, really hard task, right? It's like I usually can't do it. So here we have a data set. So there's several thousand images taken from this data set, from this web page. And so what I did is I actually cropped the faces out. I'm only looking at the face. So it's a little bit, some guys cheat. They kind of go in a muscle shirt like this or something. So I'm just looking at the face. And so on this data set, actually, it gets, on the data set that I showed it, on the data points, it gets 98.6 correct. That's not surprising, right? Because these are the images where I showed. This is an image of someone who's hot. This person is not so hot, et cetera, right? And by the way, I just binarized it. Just said above average or below average. So on the data set that I showed it, it gets, it does really, really well. But on data sets, on data points that I didn't show it, it still gets 73% accuracy, right? Which is very impressive, right? This is an extremely hard task. So what I thought is I can test this, right? Let's just see how this works. So the first thing is, this is Heidi Klum. So Heidi Klum is a supermodel. I don't know if you know her, she's from Germany. But so the question is like, what is a neural network? What would it predict if it sees Heidi Klum? And just to be clear, the labels here are -1 for not good looking and +1 for good looking. So we can now test out this image and let's see what the neural network thinks. And it's not, it's above 1. It's like, it's off the charts, right? Has the hots for Heidi Klum. It's not bad. It's not bad at all. So then, I thought, well, what about a guy, right? So I don't know who's good looking. So I asked my wife, and she's like, she didn't skip a beat. She's like, George Clooney. Right? It worries me a little that he looks nothing like me, but that's okay. All right, so let's see what George Clooney feels. So I can stick him in, and 1.2, 1.3. It's not bad, not bad. So of course, I couldn't resist, right? So how am I doing? It's like finally someone is telling me the truth, right? All right. Can watch George Clooney going down. Let's see how it does. All right, never mind. Well, and how am I doing compared to the, I need someone who's worse than me. So how am I doing compared to the ugliest person on the internet? And it's actually easy to find. You just type ugliest person on the internet into Google, and this is the image you get. That's the first hit. So I was like, all right, let's try this out. All right, well, never mind. All right, back to PowerPoint. So clearly there's something we don't understand about neural networks. That's what I pointed out. I made a lot of mistakes. Any questions about the demo? Yeah.
Once you hit a set of hidden nodes that were larger than the number of points on that two-dimensional model, why wasn't it not just fitting directly between all the points?
Why was it not fitting?
Just drawing a line directly between the points isn't that more?
It depends how I trained. I don't remember. It probably was that there was some regularization going on. Yeah. Any other questions? I have not tried this. I've given up at this point. Any other questions? All right. Okay. Good. So, why does deep learning work so well on images?
How robust is the algorithm? So suppose you take the same person from different aspects.
Oh, I have not tested this actually. I have not. Yeah. So actually, one thing I keep telling myself: this was not my best picture. Right? Could have done better. Okay. So one thing about deep nets is that they work, surprisingly well on images. And really, most of the successes actually that you've seen in the last couple years have been on images. Like even actually either object recognition, or even actually when you look at the Go player, who famously AlphaGo, actually one trick they did is they took the board and encoded it as an image, actually as a multi-dimensional image. It was like a 10-dimensional image, not just red, green, and blue. So it's like not just 3 dimensions. But so one thing that seems very, very clear is that neural networks work particularly well in images. And there was one paper that I thought, was very interesting. We got a lot of attention, and that was in 2014 by Zach et al. And they did some very interesting experiment. So they took an image, there's this ImageNet competition, there's 1 million images. And so they trained a neural network on that competition data set and then tested it on some images. And these are images that they all got correct. So this is, I think, a speaker system, this is a praying mantis, this is a lapdog. And then one thing they did is they said, okay, well, what is the smallest change I would have to make such that these images get misclassified, not just as anything, but as an ostrich, right? And just ostrich was an arbitrary thing. So these are the changes that they had to make. So they found them, and it's very easy to find them. And these images here are basically the output. So this, this image here actually gets classified as an ostrich. So this here is a speaker system. This here is an ostrich, right? So this here is a praying mantis. According to the neural network, this here is an ostrich, right? So all of these images are ostriches, and not just a little bit, but with very, very high confidence. And so this got a lot of attention, and people kind of were like, well, now this is really scary, right? Like clearly this is not an ostrich, right? So what's happening here? Any questions about this? So, and it scared me too, but for a different reason. I was interested in this setting where you go to a doctor and the doctor uses a machine learning algorithm and says, congratulations, right? Our machine learning algorithm predicts you have high risk of dying of terrible disease X, Y, Z, right? And I'm like, well, that doesn't sound so great. What can I do to change that prediction? Well, what we just learned is you can change a lot, right? You can to change the prediction, but it doesn't change jack, right? Like you're still going to die of the disease. It's just that the algorithm is going to think that you're healthy now, right? But really, nothing changed. Right? I mean, this actually did not turn into an ostrich. I don't know if people in the back can see this, right? This is okay. So I thought about this a little bit, and I came up with some conclusion. And this is my conclusion. Well, this is kind of my explanation. So one reason that neural networks work so, and this is, by the way, this is a very new result, actually. That's actually just got accepted to a conference. So you're the first big audience to see this. So this is one reason that neural networks work so well on images is because images lie on, some Riemannian manifold. So what is a manifold? A manifold is some surface that's curled up in some high-dimensional space. Right? So this here, for example, would be, it's kind of like this. Why do I know this? Well, it's quite simple. So if you take the space of all images, right? If I just take an image and I basically look at the pixels, right? Obviously, not everything in that space is a natural image. If it was, then I could just take an image, randomly assign colors to the pixels, and I would get an image of something that, like maybe my brother or something, right? Well, I wouldn't, right? It would never, ever happen. You can spend your entire life randomly sampling images. You will never get anything that's real, right? Why is this? Because the space of possible pixels, like this 16 million dimensional space of 8 megapixel images, is gigantic, but actually only a tiny, tiny part of it is actually the surface of natural images. And so why do I think it's a Riemannian manifold? Why is it curled? Well, I know it's not a subspace. Why is it not a subspace? Because if I take two images of people that are far away from each other, and I would average them. Right? Imagine you take an image of Hillary Clinton and Donald Trump, right? And you average them. You're not going to get anything meaningful, right? Because the people look too different, right? So somehow there's some smooth transition that curls up in this space, right? In this very, very high dimensional space, right? That goes all the way from Hillary Clinton to Donald Trump, or something, right? Or if you just look at bearded people versus not bearded men, right? So clearly there's a smooth transition between them, but if you just take, two people that are far away, yeah.
What makes you think it's smooth?
What do I think it's smooth? Okay, because I take two, good question. So she says, okay, all we know here is that actually globally it's not a subspace, right? But why is it smooth? Well, the idea is the following. If I take two images that are very, very similar, right? So for example, two twins or something, and I align the faces and would average them, I would actually get something meaningful. Right? So that's basically, if you or if you have a movie where you actually have very, very small changes, you can actually interpolate between them. So very, very locally, if you're a little ant, right, and you live on this thing, and you're tiny, then actually you think it's locally Euclidean. Yeah?
Your claim is for images in general, but your examples are faces. Is the claim actually for any?
So the claim is for natural images that we observe in real world. Right? Here I only took faces just because you know, I will actually show you in a minute. It's very easy to get data sets of faces. Yeah, and it's basically a sub-manifold. By the way, they don't all have to be connected. There could be a manifold of men and manifold of women, which there may not be a transition between them, right? But basically, you know, every image lies on some manifold of similar images. Okay, so that's basically my claim, and this is something actually that's I didn't come up with this. This is something, you know, this pattern theory. This is something that's been known or hypothesized for a long time. But my claim is that neural networks, what they do is they take this complicated manifold and they map it internally into a subspace. And so in this subspace now, you know, things suddenly become easy. Right? Transition between very complex settings, like, you know, do you have a beard or not? Right? This is just the example I picked here. Right? Suddenly become actually a linear transformation in the space. That's what I claim. So I told people this. I said that explains what's going on with these sexy things, right? So with these sexy, like this paper that I showed here, right? If images lie on a manifold, what's happening is if you change the image ever so slightly, you actually move it off the manifold, right? So what we're doing here is we take this image of a lapdog and we're adding some features from an ostrich on it. And so we're moving off the manifold, and that's something that the neural network has never seen, and, you know, basically off that subspace, and, you know, weird things can happen. So people go like, well, prove it. So I thought of an experiment how to prove it. So here's the idea. So I take neural network, right, and basically this neural network is trained on some data sets, and it's not even trained by me, but trained by someone else. And okay, so sorry, one more thing. Why do I actually believe that it's a subspace? Because in this space, actually, now you can train linear classifiers that work really, really well. So you can actually train a perceptron, for example, right, that just learns a hyperplane to classify bearded man from not bearded man, which is a really, really complicated concept in this original manifold, right? So you could never do this in pixel space. Suddenly, these really complicated problems become easy, and by easy, I mean linear. Okay, so here's my experiment. What I want to do is I take a new image that I know that the neural network has never seen before, and I stick it in here. So this is myself, right? So this picture was taken after the neural network was trained. So this is definitely not in there. And I don't have a beard, but what I could do is I could take a lot of people with beards and move myself into the direction of the people with beards. And if this actually works, if I'm actually right, then what should happen is I should get a beard. Right? So that's the experiment. So let's try this. So here's the idea. So I take my image, I propagate it through the neural network. Now I represent this image as all the nodes of the neural network, just concatenated. This is a really, really high dimensional vector. That's this point here, right? That encodes what the neural network thinks about me. I did not train this neural network. This is a neural network that I downloaded that other people at Oxford University trained. So this here is this point now. This is my face. Now here's what I do. I take people, a man, without beards, and I take man with beards, and I also put them through the neural network, and I do exactly the same thing, right? So I represent each one of them as all the knowledge of the neural network about this image. This is a long, long vector. And now here's the trick, right? Now I take all the people with beards and all the people with not beards, and I average their representation. So now I basically get the average bearded man and the average non-bearded man. And if I look at these two vectors, right, this gives me a direction, right? And what is that direction? The direction is the direction from non-bearded man to bearded man, right? And if this is really a subspace, right, then I can walk along that direction, and I could add beards to people, right? So let's try this, right? So I take my data point, and if I now move it to the right, it should get a beard. Here it is. Not that easily fooled. All right. So here's what I can do is I can now take this data point. This is just a whole, it's like millions of numbers, right? So, well, 100,000s actually. The question is, can I actually reconstruct an image? And turns out actually that, there is a way introduced by Gadis et al. A couple years ago, how to actually find an image that corresponds to a point in the neural network. So we can do exactly this. We can now take this point that I just constructed, which is just me plus some vector, and go backwards and generate the image that corresponds to this point. And are you ready? Let's do it. And here we go. Right, I was actually amazed that this actually worked. So we can actually, you don't just have to do this with me, we can actually do this with many things. So here's like, a bunch of people that we randomly picked from some database of images. There's Berlusconi, for example, these are famous people, there's Ralf Schumacher. And we can just add beards to them. So, but you don't actually, there's nothing about beards, right, that is special. So you can just actually make them look older. You can make their mouth open, right? You can open their eyes. You can make them smiling, right? So here, you can add glasses to them, right? Which is actually quite amazing that that works. And the amazing thing is, it's really just, I just take a point and I'm just linearly interpreting, right? So in some sense, I'm really, this is a cool tool to play around with. And my students had a lot of fun with my face, actually. But it's, really what I'm making a point here, right? The point is that there's a subspace. I can actually even do this in high resolution. So here's a really high resolution image. And I can now actually show you the movie as I'm moving this along this direction of becoming more bearded. And so here's this guy, basically, I'm moving back and forth in this space. Right? And adding beard or subtracting it. Here's, 2 pictures of me that my students had fun with. And so this basically, what you see here going to the right is like I'm going further and further and adding more and more beard, basically. You can also make me look older. So this is when I started the faculty job, this is what I looked like. This is what I'm heading. And yeah, so this is also, my students couldn't resist. So here's a picture of a little boy. You can give him a beard. And actually, but it doesn't actually always work. And so here's some failure cases. There's also, it's interesting to see where it fails. So this actually, the projector unfortunately is not bright enough. So there's a person who's Caucasian, and then the Adam beard turns out he becomes African American. And so we thought about, and this turns out actually basically what happens is here, this is very simple. The images that we found, we picked bolded man because we didn't want to add here. And so it turns out actually that this is more fashion in the African American community. So actually what we did is we had a vector of not just adding beard, but also actually making them more African American. One thing we also found is that it's actually, it doesn't work as well for women. And the reason here is actually, it's quite interesting that actually the manifold of women is much, much more complicated, of pictures of women. And none of them, there's actually a very good reason for this. So because men actually all look pretty much the same. Right? There's only a few looks that men sport, whereas actually women, they have very different hair and, very different, more makeup and so on. So, and especially actually, most images that you find online are actually people, celebrities. So celebrities actually use a lot of makeup and so on. And that actually breaks the manifold. So you would need a lot more data from them, which we don't have. So you actually get weird artifacts. Any questions about this? Yeah, sorry, yeah. Yeah.
Does your hypothesis, have you applied it to other domains than faces, for example, language?
We have actually, and it does work. So basically what we did is we took positive Amazon reviews, and then basically try to make them negative. And it works, but it breaks the language. So the one thing is, with pixels, we're not very sensitive to small changes here. But for words, if you just add one word that doesn't make any sense, you immediately see, oh, the sentence is garbage, right? I mean, at the beginning what it does, it takes a sentence, I love this razor, and it says, I love this razor not, right? So that, but then actually, as you move it more, it breaks the grammar of it. And that's just because that's too subtle. Yeah, good question. Any more questions? Okay, good. So now we can go to interpretability. So I basically try to make 2 points here, actually. The first point was when I talked about how neural networks work, that actually the building block of neural network is really, really simple. Right? It's just a hyperplane. It's just, a linear classifier. And what we do is we just multiply these matrices. What does that do? Well, in some sense, you're just having many hyperplanes. Right? You're just stretching different dimensions. So we just basically, it's like Lego blocks, right? They're very, very simple, but you can build really complicated things out of them. So the individual building block of a neural network is crystal clear. There's no question about what it does, right? So when you look at a demo, basically what it is, it just took these linear functions and just cuts them together, right? Concatenates them to basically, learn some complicated function. But the actual function that it learns at the end is often hard to understand, right? And so, for example, it completely failed at classifying me as beautiful, right? So, so lately there's been a lot of talk about, we should, people are scared of neural networks, right? Because now they can do so many things. And so in particular for self-driving cars, what they do actually have is, right, they have a neural network at the beginning, at the very front, that actually does image segmentation. So basically what it does, it detects pedestrians, detects the road, etc., all the stuff, right? And it freaks people out, right? Because they don't know how it works. And so there's been a big cry for more interpretability in neural networks. And so the questions, I try to sum up like the reasons why do people want in machine learning algorithms to be more interpretable. And so ultimately I found 4 kind of high-level reasons why that's the case. The first one is to learn more about the data. To basically say, well, my classifier can do something, right? So this, if you go back to the very, very beginning of the example with Alzheimer's, right? Let's say I actually can learn an algorithm that predicts if a person has Alzheimer's, yes or no, right? Well, the neuroscientists, they don't actually want the algorithm. They want to know how it works, right? Because they want their science paper, right? That actually, explains the mechanism of Alzheimer's, right? So that's the first part. Another reason why you want interpretability is debugging, right? Is because actually something doesn't work. Car drives against the wall, right? Then of course there's accountability. Like what if a neural network makes a mistake, right? Who is guilty? Right? Is the person who trained it, the person who wrote it, etc. And finally there's trust, and I think that's a big one, right? So people actually, before they get into this car, right, the first time they can be really scared, right? So how do you know that you can trust this thing? So let me just go over each one of these. So the first one is learn about the data. So this is something that I have a lot of experience with because I work a lot with people in the medical, I used to work a lot with people in the medical school. And this was exactly their setting, right? So basically they gave me some data, then me and my grad students, we trained some neural networks to make predictions, and then at the end, if it worked, right, they really, really want to know how does it do it. One thing I claim is that actually in this case, it's not very hard to figure out how it does it, right? And the reason is because you're working with these domain experts. And so basically you come up with hypotheses, right? And then basically what you say is, let's say you predict something in the brain, what you basically do is you can just say, okay, well, let's retrain the algorithm one more time, and let's take out this part of the brain, right? Let's make sure the algorithm cannot access it. And let's see if it can still predict it, right? And you keep doing this, and eventually you basically figure out, okay, well, this here is the essential part of the brain, and only if that's included does it work, and if it's not included, it doesn't work, right? And so there must be something in here, right? And you can do some other tests. Right, so if you're allowed to retrain the algorithm many times and just make changes to the data, right? Well, one thing you do is you take some of the dimensions of the data and you just shuffle them randomly, right? And so that now they're nonsense, right? And you see if it actually that affects it or not. So then if it doesn't affect it, this was not necessary. So I claim that we are actually at a level of interpretability that is sufficient for science, right? Because you can retrain the system, you can try out hypotheses. I don't think that's a big issue, and I've never really seen many cries there from trying to understand better how the system works. The second thing is debugging. Now that's something that's scary, right? So this here is actually a picture of the person who got fatally injured by, because he drove his Tesla on autopilot, and the Tesla actually ran into a truck, or I think it was a truck, a trailer. That was actually orthogonal to the street, right? So in this particular case, of course, the question is how could that possibly happen, right? And how can we prevent these things in the future? Now, actually, let me just actually go into this particular setting, just because you may have heard about it. In this particular setting, actually, people have analyzed what happened, and the machine learning algorithm did very well classify this object as, something on the road. It just thought it was so unlikely that there would be a truck perpendicular to the road that it basically just decided not to brake, right? And that's actually an interesting decision because these things will happen all the time, right? It actually is very, very unlikely that there's a truck in front of you, right, that's orthogonal to the street, right? It doesn't happen very often. And so it's much, much more likely that this is actually a bridge, right? And you shouldn't slam on the brake. And so there's basically a trade-off that someone had to make about, well, what if something really, really unlikely may be the case that could be really bad, right? Should I slam on the brake, yes or no, right? And there's some threshold where you have to do this, right? And the danger is that if you slam on the brake too often, the next time you drive 80 miles, down the freeway and there's some bridge and the classifier is not sure, is that an object or is that a bridge, right? It's just going to slam on the brake suddenly, right? And you will cause more accidents that way, potentially. Right? So actually it turned out that in this case, actually ultimately the decision was that it wasn't a bug, it was the kind of mistake that these algorithms make, right? And it's important to put that in perspective, right? Like there's some mistakes that algorithms make that humans would never make, right? But there's also mistakes that humans make that algorithms never make, right? So for example, humans get drunk, right? And then get into their car and are sure they can still drive home, right? Or humans try to impress their girlfriend, right? And drive 120 miles an hour, right, downtown or something, right? So algorithms don't do this. So in this particular case, ultimately, there may be some responsibility on Tesla's part, in particular because they didn't actually use a LiDAR. So if they'd used a LiDAR, it would have never happened because LiDAR detects objects. But it's pretty clear what happened. So I wouldn't consider this a bug. But let me go back to debugging. So the problem is you have some really complex machine learning algorithm that makes decisions, and you want to now make sure this works right, and you want to test it. Well, how do you do this, right? Well, how do you test other systems, right? Let's say you write an operating system, or you write some big program with 50,000 lines of code, right? Or you have an Intel processor. Let's say it's the Intel Sandy Bridge processor, 1.2 billion transistors. So how are these things tested, right? It's actually not that someone goes through every single one of these transistors and checks, is this correct, right? What they do is they actually have benchmark tests, right? That they run them over, and they make sure that everything is correct, right? And if it's not correct, then they basically go back and look into it, and then they have new benchmark sets. Well, you can do exactly the same thing with machine learning, right? So this is exactly the kind of thing you can do really, really well. You can actually run tests, run it, and if it fails them, you can retrain and do these kind of steps, right? So I claim, ultimately my point is that you have to treat machine learning algorithms as a really, really complex program, which essentially what is exactly what it is, which typically also get debugged by basically testing it repeatedly, right, and making sure it works on these unit tests. The nice thing about machine learning, actually, in contrast to traditional programming, is that you can retrain it, right? So after basically you see it fails in certain cases, you don't have to go back and read through 50,000 lines of code and see where does it fail. You just throw in these examples into your training set and you retrain, right? So debugging may actually become easier. Yeah, Greg.
So on the other hand, you have higher level abstraction and representation, like for the VHDL for the CPU or the high level program, and many of the, so it's easier to debug and test and so forth at that level. Is there an analogy?
That's totally true. So basically what he's saying is for these, it's true you wouldn't go through the transistors, but actually what you do is you have high-level representations. You say this part is the ALU, so basically this is the part is, whatever, adds numbers or something, and this here is the memory, etc. And I can test each one of these, right? So machine learning algorithms, it depends. So you don't really have this kind of level of abstraction. On the other hand, the bug is very rarely in the code, right? The bug is different, right? The bug is more that the training data does not look like your testing data, right? And that is something you can test very effectively, actually. You can train a classifier to predict, does this sample look like my training data, yes or no, right? And most of the cases, for example, this was actually a case where this was a crazy outlier, right? And you have to deal with those effectively, right? But it's a very different way of thinking, I think. Does that answer the question? Yeah. Yeah, Fred.
But in these program systems, like hardware and software, there are independence assumptions that you make. You may have characterized it as abstraction, but the essence is you can infer from carefully understanding one piece in isolation, the unit tests, that how it will work in context. And it seems that the whole essence of machine learning is that you're not doing isolation, but all the big win is in the fact that you're combining things. And therefore, your question about whether the data in the real world corresponds to the training data is equivalent to saying, exactly because we don't have independence, we have the leverage we get from machine learning. And that suggests that there's not a good analogy between how we debug complex systems that are built.
I agree. I agree completely. So this is not perfect, right? I guess my main point is that there certainly are these very complex systems that are also very hard to debug. But you're right. So basically what you could do is you could just take this part by itself and debug that part, right? And just say, well, that works in isolation. you may have,
It will work in context.
yeah, you may have some of these things, though, with local regions of the data, right? So basically, you could test your classifier on bridges, right? And it doesn't mean that it works on trucks, right? But you know it works on bridges afterwards. So in some sense, when you looked at this, remember that this little demo, where I showed, like, basically it has these little patches, like these linear patches. So if you know it works well in a certain region of the space, it doesn't tell you anything about the other part, right? But you could debug that. Okay, one thing that's important is accountability, right? So the question is like, let's say something breaks, like in this case, who is guilty, right? And that I don't really have a great answer for, right? Because ultimately I think it's a legal question, and our legal system is just so made for humans that it's hard when machines make decisions to decide these things. I think what it will lead to is something like this, where you actually have a human who's responsible. Like this is actually the solution that Tesla came up with, where they basically said, actually the autopilot, despite we call it our autopilot, is not an autopilot, right? It is just an assistant, right? And you are still responsible as the driver. And you should never, ever take your hands off the steering wheel, right? And so ultimately there's always, it's clear who's the responsible person in this case. There's two things I just want to highlight. Sorry, yeah. Actually, that's why in Europe it cannot be called autopilot. It's called something else. There's also two things I want to highlight. So one thing is outliers. So machine learning algorithms where they will fail, where they are more likely to fail, is by for data points that are really different, right? They are really, really rare, right? And they're probably not in your trained data. One possible solution in terms of legal terms is something that was done with vaccinations, like many decades ago. So with vaccinations, at some point the U.S. government made the decision that it's recommended that children get vaccinated, which is in the interest of everybody. But there's a very, very small chance, right, whenever you get vaccinated, for smallpox or something, that you actually get the disease, right? And this could be really terrible. So the solution they actually had is that everybody pays in some money into a big pot, and whenever something goes wrong, that pot of money then was used to actually compensate the victims, right? So you could imagine something similar for self-driving cars, for example, where there's basically a small chance, right, that it hits you because there's some really, really rare situation, but in some sense we kind of averaging out the risk of everybody. There's just one solution. One thing that I guess John Kleinberg talked about a few weeks ago, I think, is systematic biases. So that is a problem when you've seen this in applications in the criminal justice system, where the question was like, do convicted felons, are they likely to commit future crimes? And one thing that was very apparent is that actually there was racial biases in these predictions that the classifiers made. And that, I would still say, is an open research question, and figuring out how to fight against this, that actually these algorithms pick up these biases from the data. All right, last thing actually I have is trust. So there is this trust issue, and it seems scary to get into a car, and I'm just have this as a running example, but or get surgery done by some robot that you don't know how it operates. But I think ultimately this is something where numbers will speak. I can just make a little example. So imagine you have to go up for surgery, and this is a dangerous surgery. It's on your heart. And if you go to the hospital, there's a 90% chance it succeeds, but 10% of the cases you die. Right? There's a 10% mortality rate. You could, instead of having a human surgeon, you could also have a robotic surgeon that only has a 1% mortality rate. So it's much, much more accurate. But you have no idea what it does. Who would pick the robot? Raise your hand. All right. So you have no, that's right. That's exactly right. Very good. And actually, that's a very good point. But one thing is, you could, of course, it could be. Let me just tell you some more. Right? Let's say, the human usually fails by making some mistake in the heart. The robot sometimes is just totally off. Right? Has a weird failure mode. Instead of actually cutting out your heart, it actually cuts out your eye. Right? But it's very rare. Right? But occasionally it happens. Right? A human would never do this. Right? Who would still go with the robot? Let's raise your hand. So what if I tell you, okay, let me do one last one. What if I tell you But the robot was actually trained on people over 60 years old and does really, really well on people over 60 years old. But if you're under 60, especially under 40, there's a 50% chance it cuts your eye out. Who would still do it? Right, so your odds just went up. So I think those are the questions we have to ask, right? The question basically is, are you representative of the training data, right? And is the algorithm actually trained for you for you as a patient? Just to make an imperfect analogy, and I hope it doesn't offend anyone, but actually, when planes were first invented, and only men were allowed to fly, right? And it took a long time for women to be allowed to fly. And actually, when I was a kid, I remember, my parents talking about this, actually the first time like German airlines allowed female pilots, and some passengers walked out of the plane, right? They were like, we are all for equal rights, but not, let's not risk anything, I'm out. Right? But the irony was that women pilots were actually safer than male pilots, right? And the reason is, I don't know this for sure, but I could speculate that it was probably much, much, much harder for women to make it, right? And therefore, only the very best made it, to become pilots. So those who did make it were actually safer pilots than men. But the interesting part is that, people, just because it was different, right? People actually were scared of it. Now, this is, of course, not a great analogy because computers make very different mistakes, right? The difference between men and women actually turned out, wasn't really real. But computers would actually make slightly different mistakes. But I think a lot of the trust issue is actually just having something new that you're not familiar with and that you have to get used to. I know I'm already 4 minutes over, but I have. Okay. So let me just talk about two efforts to make machine learning algorithms. So ultimately, my point of view is that very often you don't need interpretability, but sometimes you do. And some people have actually made some efforts to make algorithms interpretable. And let me highlight two papers that recently came out. And this is something from Trevor Darrell's group in Berkeley. And this is an interesting algorithm. So here's what it does. I don't know if you can read this. This is actually trained on the Cornell bird recognition data set from the lab of ornithology. And so here what it does, it predicts what that bird is. It's a Baltimore, or I don't know what that is, Oriole or whatever. But not only this, it actually tells you why. So it actually, I don't know if you can read this, it says, this is a Baltimore, I don't know how to pronounce that word, because this is a Oriole, because this is a small bird with a black head and orange body with black wings and tail, right? So that's a very, very good description of actually that exact bird, right? And then you can actually make a lot of sense of it, right? That made quite a splash, and people were very excited about this. But actually, let me just be careful, right? So this works great on these examples, but here's actually the second most likely choice, right? It says this is a cliff swallow, which is not, because this bird has a black crown, in which it does, a black throat, which it doesn't, and a white belly, which it doesn't have at all, right? And the problem with these kind of algorithms is that, if you read the sentence, right? For humans, this seems to suggest, right, that this kind of sounds like something another human would tell you. And so you kind of think, that it seems to suggest to you that, or to us, that this is actually how the algorithm really arrived at its decisions, right? Which actually it doesn't at all, right? So the algorithm was constrained to predict these birds and to come up with plausible explanations, right? But actually, there's no reason to believe that this is really, truly the reason it predicts this, right? It could actually predict this just because it has a green background, right? And still come up with the same explanation, right? Does that make sense? So just because it sounds like something that a human would say to describe their thought process, right, does not actually mean that a machine actually has followed that thought process, right? So actually, I read that these workers, they actually took training data of birds and they actually wrote explanations, and they basically trained the algorithm to predict the bird correctly and to come up with the same explanations.
So it's not doing anything besides identifying the bird. The bird is just paired with the sentence.
That's right. The bird is, yeah, that's right. Yeah.
But it seems like these descriptions are different, slightly different each time.
Oh, yeah. So basically, it basically has some probability distribution over descriptions, right? And it draws one of them, right? So in this case, actually, you can see, you could then verify this and say, this actually something is wrong here, right? It's a colorful bird with red belly, right? Which is actually not true. So you could actually conclude that maybe there's a mistake. But you have to be very, very careful because it's really not a human who said this, right? It's just a probability distribution over possible sentences, right? Which is not really as connected as you think to actually arriving at the final conclusion. Yeah?
It seems like it's just catching on to some correlations between pixels, text, and colors and stuff, without having any understanding of the order in which these.
That's right. So that's right. It's not.
So what if we can is there anything which gives a causal model, like okay, color causes this description?
Yeah. So the problem is now so that's a good question, right? Ultimately, machine learning is all about correlations, right? All you're doing is you're discovering correlations in the data, right? So if you now find these causal things, actually, here Joe is actually the expert on this. My fear would be that if you actually try to inject, basically these kind of very clear reasoning paths into machine learning algorithms, and people have tried this, right? You take a massive hit in accuracy, right? Because you're really constraining the algorithm, right? You're forcing it to think like a human, right? Which is really not the way these algorithms work, right? They're really just function approximators, and you're paying a very high price, right? Yeah.
Is there any theoretical work in saying how there's actually a possibility for there to be human interpretable explanations of this?
There's not.
Because wouldn't it be entirely possible that although it arrives at the same conclusion, it uses a very different reasoning?
Oh, that's totally that's right. That's right. And I think it's actually that's very much a real possibility. Yeah. Yeah. Yeah.
It sounded like you might have been arguing that a bug is really just a blind spot in the data. Maybe or do you have a definition of a bug?
So it's a good point. So the bug is behavior that you did not intend. So bugs are different than the bugs in code, right? Where you basically have the for loop, the index wrong or something, right? So I think typically machine learning algorithms, it's rare that you really have bugs in the code. Right? The code is not all that complicated, actually. It's mostly matrix multiplications, and there we have these levels of abstraction that actually Greg mentioned earlier. It's relatively easy to write bug-free machine learning code because it's also not very long. It's usually just maybe 100 lines of code or something. But then the algorithm that basically that is learned, right? That could actually make mistakes that are surprising. Yeah. So those are kind of the bugs that are hard to debug, right? Yeah. Yeah.
So when you write programs, when you have exceptions, you can do like exception handling and stuff. And we can handle those exceptions because we understand what cause them. So for machine learning algorithm, if we have exception, it's different type of exception and like outliers and these kind of things. And we don't understand like what could have caused them. So how do we handle?
Yeah.
How do we make a similar?
So it's definitely true. So I guess one thing you don't just have loops where you can put in print statements or something, right? Where you actually now it does this, now it does this, right? That's just not how these algorithms work. One thing they are very good at, though, and this is something I'm also working on, but I think at this point it's pretty mature actually, is giving well-calibrated confidences. So machine learning algorithms now actually don't just they don't just tell you this is a bird. They actually tell you I believe that this is a bird, but this is probably, and then there's a distribution over the possible birds there could be, etc. That's certainly very, very helpful because that's how you can detect outliers, right? So you can actually incorporate that something, like the algorithm is really, really unsure about it. Let's say you have robotic surgery and the robot goes like, I'm pretty sure this is the heart, but it could also be your nose, right? Well, and maybe at this point stop, right? So, so I think these are the kind of I guess similar to exceptions. So this maybe there's some analogy here to exceptions in traditional programming, where you can basically catch unlikely catch situations where the algorithm is unsure and then deal with those differently. And this is, by the way, actually how, for example, flight simulators in real planes are now handled. Actually, if you have a machine learning algorithm that's only legal if there's an apparatus around it that actually catches and goes over to a traditional control theory in case actually there's some setting that actually is too dangerous, etc. Yeah.
Could debugging also look like if we have, for example, like these neurons that we expect to be doing something, but for some reason in our training, their weights keep getting zeroed out. So like, there's something in our training set that's zeroing out this set of neurons, and we had expected these neurons to be contributing something.
Yeah, no. Actually, I'm generally, so some people do this, that they look at individual neurons and say like, what does this neuron encode, and should it be on or not? I'm really not a big fan of this personally, actually. I think most of these just made great New York Times articles or something, where people say, oh, here's a cat neuron. But ultimately, this is just not how these spaces work. And it's quite simple. I can tell you why. Each neuron, essentially what it is one-dimensional space. But you could rotate the space any way you want. When you think a little bit about linear algebra, you could just multiply this with any matrix that rotates the space. And then actually this neuron would represent something totally different, but the function would be the same. So this notion of a neuron representing something is ultimately misguided, I think. And so even if you have sets of neurons, I'd be very careful with this kind of, it's very tempting, right? It's very tempting to kind of put interpretations on these neurons. But it's very dangerous because it doesn't really work that way. Yeah?
So when you suppose you train your neural network on 2 different data sets, for the people who claim that a certain neuron, like say there's a cat neuron, is it trained the same way on 2 different data sets? Or?
So if you train 2 neural networks on 2 different data sets, typically what you do is initially you initialize these neurons randomly. And so you will get 2 different neural networks that will behave pretty similar, but actually have learned to approximate the same function basically in different ways. So if you think about the demo that I showed, there's actually many different ways of connecting these dots, right? And so basically, depending on your random initialization, they will all be a little different.
So there may be 1 or 2 more questions.
Actually, I can put my last slide up here. Yeah. Yeah.
So, I'm concerned about one aspect of the interpretability, combining 2 of the examples you gave. If we ask this last neural network why it was seeing an ostrich in photos, it would tell us something that was virtually meaningless, and that gives me pause when I think about your example about the robot that tells me what it's identifying, whether it's like
Right. So there's one. So the question is like this one example I showed with this lab dog, who basically was classified as a neuron, as a ostrich with high confidence. So one thing that's very important to remember about this example is that this is an adversarial example. Like you could actually, never in your lifetime would you find an image that actually, is so perfectly created for that particular neural network to fool it, right? So if you want to make neural networks safe against attacks of some adversary, I think that's a whole different ballgame, right? And they're very vulnerable to this kind of stuff. But actually in the general case, I think these probabilities are actually well calibrated. Yeah.
Maybe we can thank the speaker for a very hot talk.
Thanks.